Welcome everyone, this is the third submodule of 3 on applications, objectives and limitations. By the end of this submodule, we will cover the LWD tools, a LWD log, applications for a motor, and the different types of RSS tools. We will then progress into a description of geosteering. The module will be completed with a look at the limitations in directional drilling. Now that we've covered measurement while drilling, MWD, it's time to turn our attention to its equally important counterpart, LWD, which stands for logging while drilling. These tools acquire formation evaluation data while the well is being drilled. LWD tools integrate the sensors directly into the bottom hole assembly, BHA, so they collect data as drilling progresses. This allows for real-time formation evaluation, which means we can make smarter decisions faster, reduce risks, and optimize wellbore placement on the fly. LWD data is typically transmitted to the surface via the MWD telemetry system. So while MWD and LWD are separate in function, they often share physical tools and telemetry systems. MWD focuses on directional data, while LWD focuses on geological and petrophysical data. Other, more advanced LWD tools include seismic while drilling, SWD, and formation pressure while drilling, FPWD. On the right of the slide, we see a typical LWD log. The first track shows gamma ray and rate of penetration ROP curves. Low gamma ray indicates sand and high gamma ray indicates shale. The next track shows resistivity. Oil is high resistance and water is low resistance. On the far right, we have bulk density, photoelectric effect, and neutron porosity curves, which are used for lithology typing and reservoir quality. Let's now focus on a tool that has been described as the bread and butter of directional drilling, the positive displacement motor, or PDM. Motors are one of the most versatile and widely used tools in the drilling industry. They have been around for decades and continue to play a vital role in directional, horizontal, and performance drilling operations around the world. A positive displacement motor is a type of downhole motor that converts hydraulic energy, specifically the flow of drilling mud, into mechanical energy to rotate the drill bit. It does this independently of the drill string rotation from the surface. In simple terms, mud goes in and bit rotation comes out. Motors are readily available, relatively inexpensive, mechanically simple and effective across a wide range of formations. This makes them incredibly valuable in all types of drilling programs, from basic kickoffs to complex multilateral wells. They are used to perform kickoffs, correction runs, sidetracks, performance drilling, and even power the RSS. Steerable motor BHAs can, in some cases, drill a complete hole section from casing point to casing point. However, this may not be the most efficient configuration if the hole section could require multiple bit trips. Now let's move on to the newer technology in directional drilling, which is rotary steerable systems, or RSS. Rotary steerable systems are downhole steering tools that allow the drill bit to be continuously rotated from the surface, while simultaneously changing direction. Unlike steerable mud motors, rotary steerable systems don't require stopping or sliding the drill string to change direction. That's a major step change in drilling efficiency and trajectory precision. Now let's look at the 4 main categories of RSS, each defined by how the tool adjusts the trajectory of the drill bit, as per the IADC. Case 1. Push the bit. In this configuration, the tool uses external pads or actuators to apply lateral force against the wellbore wall, effectively pushing the bit in the opposite direction. This type of tool is the most common in the industry because it is simpler to maintain compared to other systems. Examples are SLB's PowerDrive X6, Halliburton's iCruise, Baker's AutoTrack, NOV's Vector Edge, and Weatherford's Magnus, to name a few. This is a common type. Many of the push-bit systems on the market today have very similar methods of operation to SLB's PowerDrive. Because the pad applies a constant force, the tool changes the amount of dogleg by varying the amount of time in steering mode versus neutral mode. Case 2. Point the bit. This approach works by deflecting the internal mandrel or shaft, effectively pointing the bit in a new direction. Instead of pushing the bit sideways, the system reorients the bit face. It allows for softer, smoother trajectory changes, which is beneficial in formations where borehole quality and tortuosity matter. The GeoPilot from Halliburton was the first reliable tool to market and was seen by many as the engineer's answer to rotary steerable technology. Unfortunately, maintenance costs tend to be high, which limits their application. Also, because of the complexity, this can have a knock-on effect on reliability. Other examples are Weatherford's Revolution, the Terravici tool, and Gyrodata's WellGuide. Because the tools point the bit, they can deliver much higher doglegs compared to push the bit. They also drill a smoother borehole because the bit tilt can be varied. This is an excellent horizontal and geosteering tool. Case 3. Permanently deflected bit. In this case, the internal shaft that connects to the bit is offset inside the RSS. As the RSS rotates, the internal shaft is oriented with an internal motor to maintain the tilt in the determined direction. As the tilt is fixed, the doglegs are managed by varying the amount of time in steering mode versus neutral. The key technology is SLB's PowerDrive Xceed. Case 4. Hybrid systems. This newer class of RSS combines both push the bit and point the bit mechanics. It includes a flexible or articulated section that can bend while rotating, offering the best of both worlds. The internal shaft is deflected by using the push the bit technology, but instead of pushing the pads against the formation, they are inverted to push and deflect the shaft. As with the push the bit systems, the pad force is constant, which means that the dogleg severity depends on the amount of time in steering mode versus neutral. SLB's Archer tool uses this technology. Although not officially part of the IADC's initial 4 cases, a new generation of RSS tools has emerged with steering mechanisms located directly at the bit. This minimizes the delay between steering command and directional response. It significantly improves accuracy in thin pay zones or tight geosteering corridors. An example of this is SLB's Neo Steer, which is again focused on the high-volume, unconventional market. Let's now turn to one of the most impactful developments in modern directional drilling, which is geosteering. As our industry continues to evolve, the focus has shifted from simply reaching the reservoir to staying within the most productive part of it for the longest possible distance. That is the application of geosteering. Geosteering is the process of adjusting the well trajectory in real time, using live data from the wellbore to stay within a specific geological target, typically the most productive zone of a reservoir. Unlike traditional drilling, which follows a pre-planned geometric path, geosteering responds dynamically to actual subsurface conditions as they're encountered. In essence, we're no longer just drilling to a fixed target, we're drilling through a moving target that we're constantly updating and interpreting as we go. This matters because in many reservoirs, especially unconventional ones like shale plays or thin-layered sands, the productive formation might be only a few meters thick. If your wellbore drifts just slightly above or below this layer, production can drop off dramatically. The 2 images on the right illustrate this perfectly. In the top image, we are drilling out zone. The wellbore has exited the reservoir, potentially missing valuable hydrocarbons and reducing recovery. In the bottom image, we are drilling in zone. The wellbore is perfectly placed within the sweet spot, maximizing exposure to hydrocarbons and optimizing flow. Geosteering works by relying on logging data, which is acquired in real time and transmitted to the surface via the MWD tool. The logging data contains valuable information such as gamma ray, resistivity, density, and neutron. Often, this logging data is azimuthally focused around the borehole, enabling it to be displayed as an image. Geosteering is a collaborative effort involving geologists who interpret formation tops, dips, and bedding based on LWD data, directional drillers who execute the trajectory adjustments, drilling engineers who manage the overall well plan and operational constraints. The benefits of geosteering are that it maximizes reservoir contact while reducing drilling risk. It enables proper placement, increasing the productive life of a well. It also improves field development, where each geosteered well feeds data back into the reservoir model, improving the design of future wells. Finally, it helps optimize well spacing, target selection, and completion strategies. Now that we've explored the capabilities of directional drilling, including tools like RSS, PDMs, and the value of geosteering, it's equally important to acknowledge the limitations and challenges that come with it. Directional drilling has enabled incredible achievements, such as multilateral wells, extended reach wells, and high-precision geosteering in tight formations. However, as with any complex technology, there are real operational constraints. Let's explore these limitations in detail. 1. Torque and drag. As we increase the well's inclination and length, the frictional resistance between the drill string and the borehole wall increases. This adds torque and drag, making it harder to rotate the drill string and slide when needed. 2. Hole cleaning. In high angle and horizontal wells, it's more challenging to transport cuttings out of the hole. Poor hole cleaning leads to cuttings beds, which can cause pack-off, stuck pipe, and reduced drilling efficiency. 3. Hydraulic limitations. As the length of the step-out extends, managing mud properties becomes challenging. 4. Well control for HPHT and ERD. Well control becomes more complex in these wells due to narrow pressure windows, delayed kick detection in long well bores, and gas migration and expansion over long distances. 5. Wellbore instabilities. Directional wells often traverse multiple formations, some of which may be unstable or reactive. This leads to problems such as borehole collapse, tight spots, or shale swelling, especially in non-inhibitive mud systems. 6. HPHT tool limitations. Downhole tools, particularly MWD, LWD sensors and motors, are often limited by thermal degradation. Temperatures above 150 to 200 degrees Celsius can compromise electronics, elastomers, and batteries. 7. Unpredictable formation responses. Even with pre-drill models and offset data, formation responses can be unexpected, whether it's lost circulation, overpressured zones, or faults. 8. Steering in thin zones less than 5 feet TVD. Geosteering in very thin reservoirs, often under 5 feet in true vertical depth, is highly challenging and requires a high degree of skill. Alright, as we reach the end of this module, let's take a moment to review what we've covered and reflect on the key learning objectives in the last sub-module. We covered a variety of methods and technologies used to control wellbore direction, including positive displacement motors, PDM, rotary steerable systems, RSS, where we looked at the 4 classifications. We covered the different LWD, logging while drilling tools, and examined a typical log. We then progressed this into geosteering, where we use real-time data and earth models to keep the bit in the optimal geological zone actively. Finally, we review the common limitations in directional drilling, including torque and drag, hole cleaning, wellbore stability, and hydraulic limits. This concludes the module on applications, objectives, and limitations. Thank you for listening. The next module in this course is terminology and directional calculations, where we will introduce you to the terminology used in well planning and how surveys are calculated and presented for the different applications. This ends the submodule 3 of 3. I hope you have found it very informative. Please progress to the quiz.